Swayam Prabha. Digital India. Educated India.
Before we look at some applications, like to discuss one more material property. Obviously, this cannot be independent material property, it should depend on the previous material properties only. Okay. What is that material property? Bulk modulus of volumetric expansion. In one way analogous to what I discussed under strain, we had discussed normal strain, shear strain and then volumetric strain. Okay. And analogously here we have discussed Young's modulus, shear modulus and now bulk modulus. So, in that way they are parallel. Okay. So, normal strain, shear strain and then volumetric strain. Analogously here we discussed Young's modulus, shear modulus and now bulk modulus. Okay. Okay. How do we derive that? We consider a unit cube, okay, under triaxial compression. What is triaxial compression? Unit cube meaning cubes of unit side. Triaxial compression, we have the cube is subjected to compressive stresses, normal stresses and all of them are equal magnitude. Okay. And that is what is shown here. We have the normal stresses in x, y and z direction which are all of same magnitude. Okay. So, tau xx is equal to tau yy is equal to tau zz and minus p because it is a compressive stress. Okay. All of them same magnitude and compressive as well. Okay. And there is no shear stress. So, tau xy, tau yz, tau zx is equal to 0. Now, let us see how the equations get simplified. We will start with the expression for normal strain in terms of the normal stresses. This is the equation which you have seen. Let us substitute tau xx as minus p, tau yy, tau zz all of them are minus p. So, if you simplify you get minus p by e into 1 minus 2 nu. Same would result for other directions as well because the stresses are same. So, the normal strain in all the directions are same. So, epsilon xx is equal to epsilon yy is equal to epsilon zz is equal to minus p by e 1 minus 2 nu into 1 minus 2 nu. Okay. Now, how did we define volumetric strain? Fractional change in volume by original volume, and that we related to the sum of the normal strains epsilon xx plus epsilon yy plus epsilon zz. So, if you sum this 3 times you will get 3 into minus p by e 1 minus 2 nu. Now, how do you define bulk modulus? Bulk modulus is denoted by capital K, is the applied stress which is minus p divided by the fractional change in volume. So, applied the stress is minus p and the fractional change in volume is minus 3 p by e into 1 minus 2 nu. If you simplify you get e by 3 into 1 minus 2 nu. Okay. That is the expression for bulk modulus. As I told you, it cannot be independent property. The bulk modulus is depending on E and nu. Okay. There can be only 2 independent properties. Okay. And what is the name of more formal name? Bulk modulus of volumetric expansion or elasticity, if you want more formal name for K. Okay. And what is the significance if K is very large? Okay. For the same stress the volume change will be very less, same like our Young's modulus and shear modulus also. What did we say? If our Young's modulus is very large, for the same normal stress the normal strain is very less. Similarly, what do we say for G? For the same shear stress, material with larger G will have a very small shear strain. Similarly, here for the same applied stress, the material with higher bulk modulus will have very small volume change. Okay. Okay. So, for the case of Young's modulus, higher Young's modulus, lower normal strain, higher shear modulus, lower shear strain, and higher bulk modulus, lower volumetric strain. Okay. What we will do now is look at some applications of the equations which we have discussed and derived. Some simple numerical applications, they are not conceptually difficult. I would say just simple substitution examples only, but they will help us to get a feel for what the equations are, how are they used, etc., and some range, some idea of the range of numbers, some idea of the range of the values for the different variables which I have come across. So, what are the applications? The same equations will be used in different ways. Okay. So, first application is to use these equations to determine material properties. Okay. Once again, same set of equations to find strain, same set of equations to find stress. Okay. Okay. So, now let us read the example. An element of nylon is subjected to triaxial stress. I think we have come across this triaxial stress few times now, which means only normal stresses are applied. Find the material properties for the nylon if the following stress and strain data is known. The normal stresses are given, okay, tau xx, tau yy, tau zz, all of them are compressive, okay, and the normal strains in the x and y directions are given, epsilon yy, epsilon xx and epsilon yy are given to us. In terms of units, the stresses are in terms of Pascal, they are megapascal. Okay. They are force per unit area. So, the unit is in terms of megapascal. In terms of for the strains, they are dimensionless. So, a number. Okay. The value is minus 740 10 power minus 6 minus 320 10 power minus 6. So, they are small values. Okay. We said we are going to analyze under very small strains. Okay. And so, these numbers cannot be very large. Okay. 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 So, what are the properties we are going to determine? Young's modulus, Poisson's ratio, rigidity modulus, bulk modulus. In fact, all the properties which are discussed can be determined. Okay. So, let us write the equation for the normal strain in the x direction in terms of the normal stresses, okay, and the left hand side epsilon xx is given to us minus 740 10 power minus 6, E has been taken to the left hand side, okay, and right hand side we have tau xx which is minus 4.5, and then minus of tau yy plus tau zz, that is this plus this and then a minus sign will give us 5.7 and then nu. Remember, E is in megapascal, same unit as tau. Let us write down the equation for the normal strain in the y direction, and for the y direction normal strain, remember you have tau yy here and tau zz and tau xx are here. So, epsilon yy is minus 320 10 power minus 6 and of course, E to the left hand side, and then tau yy is minus 3.6 and these sum together to minus sign gives 6.6 nu. So, now we got two equations in two unknowns E and nu, the two properties Young's modulus and Poisson ratio. So, solving simultaneously we get E as 3000 megapascal, a large value usually expressed in terms of gigapascal. So, 3 gigapascal, okay, and nu if you solve you will get as 0.4, and once you get two properties we know that we can get all other properties. We have only two independent properties, we have solved for the two independent properties. So, we know the relationship between the shear modulus E and then nu. So, simple substitution will give you the shear modulus 1.07 gigapascal. We can also find out the bulk modulus, we know E and then nu, when you substitute we get 5 gigapascal. A very simple example based on experimentally applied forces expressed as per unit area, which are the stresses here, and the experimentally measured strains. We are able to determine the material properties, in fact all the material properties, Young's modulus, Poisson ratio, rigidity modulus and bulk modulus. Okay. The next example is for determination of strains. Okay. So, we have an element of steel in the form of a rectangular parallelepiped of dimensions 300, 150, 150 mm, okay, that is what is shown here. A is 300 and B and C are 150 mm. It is subjected to triaxial stress as we have discussed earlier, and here again all the stresses are compressive 60, 40 and then 40, and they are acting on the x, y and z faces. And what is it we have to determine? Determine the changes in the dimensions of the element. Once we find the strain, then we can find the change in dimension and also find the change in volume. Okay. To proceed further, we need to be given the properties. Two properties are given, any two properties can be given. What is usually measured and reported is the Young's modulus, very well known property to all of us, and Poisson ratio. That is why typically you will see Young's modulus and Poisson ratio being given as a data to us. Okay. And look at here, steel has 200 gigapascal as Young's modulus. In the previous case it was 3 gigapascal, when we solved we got 3 gigapascal. So, steel has a much higher Young's modulus, which means the change in dimensions are going to be much smaller. Okay. Okay, so change in dimensions and volume. So, let us write down all the data given in the question. First the dimensions of the block, next the normal stresses and the material properties. To find out the change in dimensions, we will have to find out the strain, the normal strains. So, epsilon xx is equal to the expression which we have derived in terms of the three normal stresses. So, all the values are available. As I told you, these examples are not conceptually difficult, simple substitution examples. So, simply substitute, we will get minus 180 into 10 power minus 6. Of course, all the stresses are compressive, we have a contraction in the dimension, and to find out the decrease in the length we will have to multiply epsilon xx with the dimension. So, the dimension along x direction is a. So, we multiply epsilon xx with a to get minus 0.054 mm. Okay. That is the decrease in the dimension along the x axis. So, similarly let us do for the y direction. So, write the expression for the normal strain along y direction. simple substitution will give you the normal strain along y direction multiply by the dimension along y direction will give you the decrease in the dimension along y direction, which is minus 0.0075 mm. Okay. And epsilon zz similarly substitute in the expression, and the normal strain is same along both y and z direction. To find the change in length, multiply by c, in fact c is same as b. So, we get the same decrease in length. Look at the change in length, they are very small, usually a scale as let us say 1 mm division, and this is 0.0075 mm or 0.54 mm. So, these are much smaller than our usual scale dimension, the least count of a usual ruler scale. Okay. To find out the change in volume, we will have to find out the delta V by V, the fractional change in volume, which is sum of all the normal strain. So, we have found out all the 3 normal strains. When you sum up, of course 180 plus 50 plus 50 gives you 280 minus 280 10 power minus 6. To find out the change in volume, we will have to multiply this fractional change in volume or the volumetric strain with the original volume, which is ABC, this is cuboid, okay, which gives us the decrease in volume. So, minus 1890 millimeter cube. So, what does it mean? If you subject this cuboid to these normal stresses, they are compressive. These are the decrease in dimensions along the XYZ direction, and this is the decrease in volume. Okay. Remember, when we started off, we said we are going to look at solids which are not perfectly rigid, they are deformable solids, and we have an example here. When you subject to this body to these forces or force per area, visually you may not observe any change, but there is decrease in dimension along the 3 direction and a corresponding decrease in volume of the whole object. Okay. That is why we have discussed deformable solid bodies. Not if you are discussing a rigid body, then these dimensions will not at all change. Okay. That of course is an ideal condition. More realistic condition is where there is change in length and volume as well. Okay. The last example where we are going to determine the stresses. Okay. So, a cube of granite with sides of length 75 mm is tested in a laboratory under triaxial stress. Gauges mounted on the testing machine show that the compressive strains in the material are epsilon xx and epsilon yy, epsilon zz. The normal strain along the x, y, z axis are shown. These gauges are called strain gauges. They can give us the strain, they can be used to measure the strain. That is why we said strain as measurable. Okay. Determine the normal stresses on the x, y and z faces of the cube. So, once again we need to be given the material properties. E is given as 60 gigapascal and nu as 0.25. Okay. So, let us find out the Lahm's constants g and lambda, so that it becomes easy to calculate the stresses. G is E by 2 into 1 plus nu. So, if you substitute, you will get 24, and of course, unit is same as E gigapascal, and lambda, if you substitute in this expression for lambda, E is known, nu is known, you will get 24. The unit is once again same as E, which is gigapascal. Okay. So, G is 24 gigapascal, lambda is also 24 gigapascal. Okay. The expression for stresses involve the divergence of displacement field which is sum of the 3 normal strains, and so we are given the values of 3 normal strains. So, simple substitution will give you this value for the sum of normal strain, which is same as divergence of displacement field. So, once you got these values, simple substitution, okay. We expressed the normal stress in terms of the normal strains. So, simple substitution, we found out the value of G, we found out the value of lambda. So, we will get minus 64.8 megapascal, okay. And similarly for tau yy, simple substitution will give you minus 43.2 megapascal, and similarly for tau zz we get minus 43.2 megapascal. Of course, all of them are compressive, and remember the unit is megapascal, the unit of G and lambda are gigapascal. So, when you express you get in terms of megapascal, okay. Usually the stresses, as we have seen in all the cases, are in terms of megapascal. The property E, G, etc. are in terms of gigapascal, okay. Okay, to summarize what we have done is discussed Hooke's law, which is the stress strain relationship. Why did we discuss that? We want to express this viscous stress in terms of the velocity gradients or the strain rate, which is the Newton's law of viscosity. But to understand that, we took a diversion to solid mechanics the third time and the last time, and discussed the stress strain relationship, so that you can extend that to stress strain rate relationship, okay. Okay. In terms of summary, we discussed the relationship between stress tensor and strain tensor, that was our objective, or the components of stress tensor and components of strain tensor. Now, we can understand that statement much better, but that relationship is material dependent. That is where we started off. Because it is material dependent, we had to discuss the assumptions. What are the assumptions? Assumptions are homogeneous, isotropic, linear, elastic, solid, okay. And we also discussed different material properties, namely Young's modulus, shear modulus, Poisson ratio, bulk modulus, okay. Then we derived the Hooke's law, strain in terms of stress, then stress in terms of strain, and what is it we achieved? Expressed stress tensor, the components of stress tensor in terms of measurables, which are the strain, or still more in terms of the displacement gradients. That is a major, I would say, objective and achievement what we have done here, expressing immeasurable in terms of measurable quantities. Also finally looked at some applications, very simple applications. In terms of determination of material properties, strain, stress, same set of relationship, something is given, something is not given, okay, and we found out what is not known to us.